Alright guys, as promised, I told you I'd make a video of these notes real quick for those of you who were absent, since so many of you were gone on Friday, and for those of you who came in late. So I'm going to fly through these notes real quick. Again, we're just going over the basics of exponential functions. We're not really going into solving them yet. So I just want you guys to get a feel for what these functions are and what they look like. Okay? So as stated before, this is our main form. Just like how linear functions have y equals mx plus b, which is slope-intercept form, these functions go by the form y equals a times b to the x. Again, where x is in the exponent location and b is the base. So anytime we have an exponential function, x has to be in the exponent. X doesn't have an exponent, x is the exponent. So make sure you understand that process. Now if we take a look at the graph, we can see that these functions, these exponential functions, they don't look like linear functions anymore. We know linear functions are a straight line. Exponential functions, on the other hand, curve. Alright, they start out pretty slow and then they get going pretty quickly depending on what the base is. So again, that's our first observations. These lines are curved. Okay? They don't have a constant rate of change. And again, that's the biggest thing that differs between exponential functions and linear functions. Linear functions have a constant rate of change, otherwise known as the slope. Exponential functions don't have a constant rate of change. They don't always go up by 4. They don't always go down by 2. They actually have a multiple or a factor that they go up by, and we'll talk about that soon. Another thing, notice how these functions start off slow. They're not increasing much at all. But once they hit the y-intercept, they shoot up, depending on what their base is. So again, these things start out slow, but then they gradually start increasing faster and faster and faster. Just like how in class I was talking about a zombie apocalypse, in case it ever happens. One zombie turns one zombie, then those 2 zombies turn 2 more zombies, then those 4 zombies turn 4 more zombies, then those 8 zombies turn 8 more zombies, then those 16 zombies turn 16 zombies, and so on and so forth as it goes 32, 64, 128, 256, 512. You get it, okay? As the number gets higher, it starts shooting up rapidly. It starts going up very quickly. That's what these functions are doing. Also notice, one thing I may not have mentioned in class, but I want to point out right now, look at these bases. A base of 10, a base of 3, and a base of 2. Notice how the base of 2 doesn't increase as quickly as the base of 3. And look how the base of 10 shoots up the quickest. The larger the base, the faster the increase. Again, that's an important characteristic to understand of these exponential functions. The higher the base, the quicker that it's going to go. Okay? Next. One of the big things you guys are going to have to understand between linear functions and exponential functions are telling the difference between the two on the EOC. So as I look at these two charts, I see one chart, -1, -3, -9, -27. I see the other chart, -1, 1, 3, 5. I want to figure out which one is an exponential and which one is a linear function. Now if I go back to one of the main characteristics, exponential functions don't have a constant rate of change. If I look at the second graph, or sorry, not the graph, but the chart, this second chart increases by 2, increases by 2, increases by 2, and I'm sure it's going to follow that pattern all the way down if we were to extend it. This has a constant rate of change. Since it has a constant rate of change, or a slope, constant slope, it is going to be a linear function. That means the first chart has to be exponential, but let's look at why. If I look at the rate of change, this is going down by 2, this is going down by 6, this is going down by 18. Now, you probably may notice a pattern within how much it's decreasing by, but again, this rate of change is not constant. If you dive further, you may see Mr. Z. Negative 2 times 3 is negative 6. Negative 6 times 3 is negative 18. Negative 18 times 3 is going to be negative 54. That is what we're multiplying by. That really is what the base is going to be. Again, we're not worried about building functions right now. We're mainly worried about just telling the difference between these two. We'll get into building functions next week when we talk about geometric sequences and arithmetic sequences. But again, the rate of change is the main telling point between whether it's linear or whether it's exponential. So again, this is exponential. And you'll see notes coming up on this process. It shouldn't take you guys long at all because, again, we've already covered it. Now, next, the other part that you guys have to know for this EOC coming up in June is how to use exponential functions, mainly in growth and decay problems. So again, this is our main form, where B is the growth or decay factor, and A is the starting value. If you can remember these two things, you should be good to go. So, as I read through the first one, it says, since 2005, the amount of money spent at restaurants in the United States has increased by 7% each year. In 2005, about $360 billion was spent at restaurants. If this trend continues, how much will be spent at restaurants in the year 2015? So, the dead giveaway that this is an exponential function and not a linear function is that we're increasing by 7% each time. 7% is going to be part of our growth rate. Again, if it said it increased by 7 billion each year, that's a constant rate of change. But again, remember, percents cannot be constant rate of changes, because you could go up by 15 one year and then 25 the next year. That's not constant. So again, I'm going to use my function y equals a times b to the x. I know that my starting value is 360 billion. I know my growth rate is 7%. I am not going to put a 7% there. I understand 7% is the rate that it's increasing, but again, I don't want to find 7% of the item. I want to find, or the amount, I want to find the amount plus 7%. So if you remember from last year in 7th grade, that we could find 7% and then add it on, but that's 2 steps. Again, we're all about working efficiently. So to get rid of that middleman, I want the total amount, which is 100%, plus the 7%, which leaves me 107%. And again, if it started in 2005 and we want 2015, my time has to be 10 years. This brings up an important tip for exponential functions. If we're talking about growth rates, it's always going to be 1 plus the percent. If we're talking about decay rates, it's always going to be 1 minus the percent. So again, I'm not putting 7% here. I'm putting 1 plus 7% here. Again, I'm not going to multiply first. I'm actually going to figure out what this is. But again, you can just plug this entire thing into your calculator right away. I have to use my phone right now because I don't have a calculator at my place. So I know that I want to raise 1.07 to the 10th power to the 10th. Delete that to the 10th. And I want to multiply that by 360. And I'm going to get 708.17 billion. $708.17 billion. And that's your answer. Again, just plug this thing as you see it. Remember, if you want to get to this exponent area in the calculator, you have to use a caret. The caret will put you in the exponent place. Hit enter and you're good to go. Next one. It says, suppose that in 1985 there were 285 cell phone subscribers, because obviously in 1985 no one had cell phones. The number of subscribers increased by 75% each year after 1985. How many will there be in 1994? So again, y equals a times b to the x. My starting value is 285. My growth rate is 75%. So again, 1 plus 75% is 1.75. And then 1994, from 1985 to 1994, that's 9 years. So, do the same thing. I'm going to raise 1.75 to the 9th power, and then I'm going to multiply that number by 285, and I'm going to get 43,871 or 72 subscribers. Again, guys, it's just using the exponential function, y equals a times b to the x. Plug in your starting value, plug in your growth rate, plug in your time, and then we're good to go with 43,871. So, all these are done the same way. If you turn to the back, we no longer have growth, we have exponential decay, but these are done the same way. Again, we're going to use y equals a times b to the x. You're going to plug in your values, and then you're going to figure out the decay. So you can hit the pause button, do these on your own, but the majority have already done them, so I'm going to go through these pretty quickly. If I'm looking for my starting value, it's going to be 101 kilopascals. If I'm looking for my decay rate, it says that it decreases about 11.5% for every 1,000 increase in altitude. So if I do 1 minus the percent here, since we have a decay, if I do 1 minus the percent, I'm going to have 0.885. Now, if you're looking for our x value, if you're looking for the time frame or the number of times it's going to decrease, for every 1,000 meter increase, it decreases 11.5%. So if I have an increase of 3,000 meters, that means this is going to happen 3 times. So x is going to be there. So if I do, where's the clear, 0.885 raised to the 3rd power, I am then going to get 0.69. I want to multiply that times 101, and I'm going to get roughly, approximately 70 kilopascals. Again, guys, same concept as growth, except now it's a decay. Next one, it says the population of Shenanigansville-topia is 45,000, and it decreases 16% each year. If the trend continues, what will the population be after 15 years? Starting value is 45,000. My decay rate is 16, but again, it's 1 minus the percent, so it's going to be 0.84. And then 15 years, plug it in. Once you do your math, you should come up with the answer. I'm going to raise 0.84 to the 15th power. I am going to hit enter. I get 0.07. I'm going to multiply that by 45,000. And I'm going to get 3,291 approximately people. Because again, we're talking about population. So I guess in 15 years, no one loves living in Shenanigansville-topia. I don't know why. It's probably the coolest name ever for a city. Yet there's only 3,291 people left. So that's decay. Same concept as growth, except you're going down, you're decreasing in value instead of increasing. Now, the last big real-world application to exponential functions is going to be compounding interest. Now, this is what happens when you guys take out loans. So, for example, when you start going to college, let's say you're applying to college and as a senior and you want to go to some expensive colleges, you guys have already done that project, you have to pay all that money back. That's why I harp on it, guys. Look for scholarships as often as possible, as much as possible. Apply to every single one you see, because if not, you're going to have to pay and pay and pay once you start applying to college. So, compounding interest is how you're going to determine how much money you're going to have to pay back. So, for example, the first one, it says, suppose that when your friend was born, your friend's parents deposited $2,000 in a bank account paying 4.5% interest compounded quarterly. What will the account balance be after 18 years? So how much money will be in the account? The account starts at $2,000 and it gains 4.5% interest compounded quarterly each year. This is a formula you're going to have to understand how to use. I understand I said y equals a times b to the x, where a is the starting value, b is the growth rate, and x is the time. This pretty much takes that form. We know p is the principal amount. 1 plus the rate, guys, that's just a growth rate. But this n is slightly different. This is how often it's compounded. Same with this n right here. And t is, of course, time. So when you're using this, again, you're just looking for the variables inside the word problem and you're putting them down on paper. So I know my starting rate is, well, sorry, my starting value is 2,000, just like my A. That's what P is. I'm looking for 1 plus the rate. The rate is 4.5, so 0.045, because again, you have to convert the percent to a decimal, divided by the number of times it's compounded. It says it's compounded quarterly. Compounding quarterly means it's compounded 4 times in a year. Again, 4 times in a year for this n. The time is in years, and it's 18 years. So, if I do 2,000 times, I need to do 1 plus 0.045 divided by 4. So 0.045 divided by 4, I get 0.01125. I'm going to add that to 1. It's going to be 1.01125. 4 times 18 is 72. This looks exactly like y equals a times b to the x now. Again, y equals a times b to the x. We just had some slight work beforehand. So I'm going to raise that value to 72. And then I'm going to multiply that number times 2,000. And you should get your answer, which I got something incredibly wrong. So let me type it in one more time. 1.01125 raised to the 72nd power. There it is. I don't know what I did wrong the first time. Multiply that by 2,000, and I get $4,475.53. Again, notice you start out at 2,000, you end up with 4,475. Guys, that's why you put money in a savings account that accrue interest, because again, you got $2,275 just doing nothing, just having your money sit there. So that's why it's important to also have money in savings and invest so you get that interest accrued upon. Last one. You are investing in your friend's startup company, Cheese, and Cheese. It sounds like a stellar company. I don't know why you wouldn't invest in it. You invest $3,500 because you're a baller, and due to your intuition, you actually earn 6.7% interest compounded monthly. What will the balance be after 1.5 years? Let me make a statement real quick. 1.5 years, guys, this time frame is always in years. If you ever get a question that says 18 months, 24 months, make sure you don't use 18 or 24. Make sure you convert that to years. So, finally, I'm going to use my compounded interest formula. My starting value is 3,500. 1 plus 0.0675. Compounded monthly means 12. 12 months in a year. 12 times 1.5. So I'm going to have 3,500. If I do 0.0675 divided by 12, I get 0.005625. I'm going to add that to 1. I get 1.005625. If I do 12 times 1.5, that's going to be 18. So I'm going to raise 1.005625 to the 18th power. And then I'm going to multiply that number times 3,500. And I'm going to get 3,871. That is a terrible amount. Of course, it's only after a year and a half, so after a year and a half, you gain roughly $371 for doing nothing. So, again, if you left this money in a lot longer than 1.5 years, I'm sure this number would grow and grow and grow. That's why the longer it stays put, the more money you can get. So again, guys, that is compounding interest. This is everything you need to know for exponential functions in terms of Math 1 when it comes to comparing to a linear functions and when it comes to using real-world applications. There are still a few other minor details we have to cover, but again, those notes are going to come later. So, hope you followed along. Hopefully it was easy to understand, and I'll see you guys later.